All right, so why don't we begin? There are some issues with, I guess, the Meraki's and other stuff where it's blocking screen mirroring traffic for devices, so I don't have use of my pen because I was doing that from the tablet. So I'm gonna have to go from the laptop and use the board to go over. That's impressive. To go over um, stuff that I otherwise would have used the pen on the tablet to do. So I apologize for that. I'm not sure when that's going to get fixed. The real solution is for the screen um, computer to act like an access point so you don't need the network because it's blocking some device traffic. Okay, so why don't we get started? I still promise I have to do the proof of the variance for the geometric distribution. I'll just do that on the board on Tuesday, on Thursday. Today's Tuesday. On Thursday, um, because I wasn't expecting this pen issue to be a systemic thing. All right. So let's talk about the Poisson distribution. The reading by Friday the 8th, please make sure you're getting not many pages, just 3 pages read on the Poisson distribution, but please make sure you're getting section 3.4.5 done. Again, I recognize that the main text is fairly terse, and so make sure to supplement that with things you find, whether it's Khan Academy or YouTube or whatever. There are many sources for material that might resonate with you better than what the book is. Okay, so the reason for choosing this book is because I stretch the cost of the book across 2 semesters, and so data analytics will make use of the same book so that you're not paying twice for 2 different books. All right, so I think I might have displayed this before, but this is an example of a system that does customer tracking. And if you think about what happens, well, the setup is you have a camera, and that camera is overhead for the entryway or entry box for a retail establishment. As you can see, it tracks people as they come into the store, and it tracks people through the entry box as they leave the store. And one of the things you'll see is the counts in the upper right-hand corner, your right of the interface. You'll see the number of folks that enter in a given period of time, and the number of folks that exit are constantly incremented. And the difference between the number that enter and the number that leave are the number that are inside the store. And so, you can imagine a retail establishment might want this because with this, you can actually model quite nicely um, how customers enter the store, and you might use that to influence your staffing levels based on data that you observe. And as you can imagine, for a particular store, this traffic has periodicity to it, and by that I mean that the number of customers that enter, say, a coffee shop might change. You have a big rush in the morning, then maybe you have a big rush again at lunchtime, then maybe you have a big rush in the afternoon, and then in the evening it peters out unless you're near maybe a college campus or two, and it might um, uh, you might see a rush and late at night. And so, the ability to track things in time and maintain counts for things in time is a very important quantity. And today we're going to talk about the Poisson distribution, which is purposed with the probability of the number of events that happen in time for some standard unit of time. And so next is a kind of segue to this idea of tracking things in time, but you can also track things in space. And this is to kind of show you a little bit of some of the applications for what we're after in this course and the following course next semester. In this example here in the top frame, you see an overhead camera view. The video is a little bit grainy, but that's not the important part. And you can see this yellow path drawn on the image, and that yellow path represents the location of a subject as he or she walks through the store. And now you're not necessarily concerned about loss or security, things like that. You're in this case concerned, excuse me, about what parts of the store your customer visits. You can take that raw information, like you see in the top frame here, and on your lower left, you'll see this diagram. So you can take the position over time and say, okay, well, how many times does someone enter the store in a particular location? And then you can maintain those counts and then construct what's called a heat map. And that thing in the lower left-hand corner is a heat map. And what that heat map depicts is anywhere from blue up through red. Blue represents cold, and red represents hot, and colors in between represent different quote-unquote temperatures. And so what you find is that the more frequency or the higher the counts associated with the floor space where people are more, you can have higher counts for those locations based on a tracking system like this, and therefore you're going to have, excuse me, hotter spots. Excuse me. You're going to have hot spots in that part of the uh, of the image, and what that tells you, excuse me, what that tells you is that there's some parts of the floor where more customers walk to and browse or they attend to in the store. And certainly, you can also look at things like the number of customers that might be at certain registers and also the amount of time each person spends at certain registers. And you might use that to determine whether or not you should have more registers or if there are any bottlenecks in the store, because certainly you don't want to frustrate your potential revenue stream at the point of sale because they might just decide to leave their items and walk away, and that's a missed revenue opportunity. And so this is used all the time, and you can look at the arrival and reason over the probabilities associated with arrival in time or in space, right? It's not just the fact that they come into the store, but also things like where in the store a person might be. Okay, so this is a larger example of a heat map, and you can see a bunch of shelves, and it's kind of like a typical in the top. The top view here is not the same um, uh, retail establishment as this bottom right-hand view, but the top view is a typical supermarket setup. You can see the entryway, the doorways here, and then you see what might look like the produce section, right? And then you see the stacks or the shelves, and you have cut-throughs between the shelves, in this case, instead of long aisles. And then along the back end would be like your freezer section where you'd have like, meat and stuff like that. And then you have along the top end, you have some other stuff, maybe other cold items or frozen goods. And then you have the registers here on that side. And you notice there's some locations that are more bright red and other locations that are more blue. The hotter spots are the red and the yellow, and the colder spots are the blue. And one of the things you notice here is that people tend to spend a lot of time in the produce section, right? And the produce, of course, people, pick up the produce, look at the produce, and select something to his or her liking. And then you'll notice here the end caps, the end of these shelves. You can see a lot of hot spots because people tend to, their attention is caught at the end caps. And so when you design a supermarket or when supermarkets are designed, um, they do certain things deliberately. They place things in the floor space based on where people are going to more frequently be. And in fact, a supermarket can actually tell you if you have a new product and you talk to the supermarket management or ownership or what have you, and say, hey, I have this new item. Can you sell it? They're going to want to cut a price with you and make deals based on how popular they think your item might be. And so the more popular items, things that are going to sell better, they tend to have in the more high traffic areas. Why would you associate some item that doesn't have high value in a part of your store that doesn't have high value? And as you can imagine, parts of a store that have high value are those places where people are going to visit that part of the floor space more frequently than others, because the more literal eyeballs that you get looking at your product, the more likely that someone is to make a sale. And so everything in a supermarket is specifically designed to separate you from your dollars, right? You'll notice in things like the cereal aisle, about maybe 3 feet off the ground, 2 to 3 feet off the ground, well, more like 3 feet off the ground, you see things like Fruit Loops, Lucky Charms, the kind of quote unquote children's cereals. And the reason why they're 3 feet off the ground is because that's about a child's um, eye view in terms of their height, right? And then you see more, the stuff with a lot of fiber and wheat and stuff like that is about maybe 5 feet to 4 feet off the floor in terms of the height of the shelf, because that's about an adult's eye view, right? So whenever you go to a supermarket, you'll notice, certain things, and the floor space is designed very deliberately to try to capture income. And one of the things they use is tracking to try to make sure that they can maximize the floor space. Another trick that they use, not trick, I shouldn't pose it that way. Another strategy that they employ, you notice certain items that should go close together are very far apart. Like the peanut butter is never right next to the jelly, right? You think, gosh, well, people have peanut butter and jelly all the time. Or peanut butter and bread, why not put them close together? It's on purpose because by getting you placing one item at one end of the store and the other item at the opposite end of the store, it forces you to walk the length of the store in order to find those two items. And in walking the length of the store, there are more opportunities for you to see other things that you might not otherwise have purchased. And so it's all purposed with trying to get you to spend more. And then the bottom, there's a typical electronic store, like a phone store. And as you can see, there are hotspots associated with areas of the store that people visit more frequently. This device is a pretty interesting one. It's called an eye tracker. And what this eye tracker does, it has a forward-facing camera to view video associated with what the user sees from his or her eyes. And then there's another camera backwards facing into the eyes of the subject. And this thing measures the position of the eyes, meaning what you're looking at. And so these eye trackers come in all sorts of forms. This is just one example. And they use this sort of tracking of position in space in time to design things like packaging. And so here we have typical packaging for a steak meat item. And what they'll do is they'll design a package and they'll test out to see, what people look at first, what people look at second in time. And they'll actually use such data to maximize or make more efficient or better or effective the packaging for all sorts of items. And so you get a bunch of subjects and you outfit them with these eye trackers, and then you run the experiments and actually measure their eye movements, what they're looking at first, second, and where they're spending the most time. And so in this case, again, you get a heat map. And this heat map says in terms of position as well as space and the coloring, if you will, the more hot it is or closer to red, these colors, it represents the frequency at which their eyes were looking at a particular position for this package. And so here you'll see the first thing that they do is they look at the product itself, they look at the meat. And so part of the optimization is, of course, they made sure that front and center is as much of the item itself, because you want to look at the product that you're buying to try to assess whether or not it's something that you desire to purchase. And then the second place where the eyes attend is somewhere on the label. And so then once you look at it and say, wow, I think I want to buy that, you want to kind of make sure what it is. All right, what type of cut it is. Maybe it's the expiration date, all sorts of stuff, the package date, and stuff like that. And then after that, a little bit more about the description. And so people use this idea of tracking in time to talk about or optimize package design. And so this is just to kind of show you a little bit of applications of the type of things that we talk about. But we'll segue now to the actual Poisson distribution. Okay, any questions about this? All right, a lot of interesting things. And so retail uses a lot of stuff that we talk about in various ways this semester and next in data analytics, as well as logistics, all sorts of things. Everyone is data driven these days, and it's only going to increase. Okay, this is one last example. This is a Best Buy store, and this is the view from an eye tracker as it pertains to when you first walk through the doorway. And you'll notice during certain times of year, they will have certain items in certain locations for the experience you have when you first walk through the doorway. And so you'll notice here, given these hotspots, people generally direct their attention towards the center, and then they spend a little bit of their eye movement looking off center to the left and right, and then you'll look at some of the signs above to figure out what departments are where in the store. And so sometimes you'll see, like, for example, if you walked into Best Buy recently in the last 2, 3 weeks, you might see the Fitbits in some display in some section of the store. Cell phones are high money items for stores, so you'll see the cell phones just beyond to the right of the Fitbits. During the holidays, you might have like smart TVs right as you walk through, and all of that is on purpose, and it's done in negotiation with the vendors of those objects because they all vie for product placement in the better locations of the store. Okay. Any questions about this? Yeah. So this is for real, right? People use this to make money, and they use this to optimize, and they're constantly changing the positioning of things in order to try to maximize revenue. Okay. So let's talk about the Poisson distribution. And the Poisson distribution is a probability, it's a discrete probability, excuse me, and it traffics in events that happen in time. And what the ask is for Poisson is the probability that you observed a certain number of events over some assumed unit of time. And so with the Poisson, you could certainly design and simulate a system anywhere from a coffee shop to looking at locations of things with a little bit of engineering. Okay, so let's use the physics eyeball, right? You observe something, right? Because after all, some event occurs or some experiment or trial is run and you make an observation. And let's say you make that observation and, in the case of this, picture, some event happens. Maybe the dog walks into the yard. Maybe the squirrel runs down the tree, or maybe the customer comes into the store, like the example that we saw at the outset with the coffee shop entry box instrumentation. So you observe something, and you make this observation not arbitrarily. Over some standard unit of time, delta t, you're going to make an observation. So this event occurs, event occurrence is represented as a single dot here, right? And it doesn't matter what that dot is. It could be, as I said, the dog walking into the yard, could be the customer walking into the store. It doesn't matter. What matters here is that you have some standard period of time, or sometimes in the literature, it'll be described as a window of observation. And this window of observation, delta t, can be any standard unit, but it must be consistent over all your observations. So you might say, okay, well, my delta t is 1 minute at a time. It might be 5 minutes at a time. It might be 15 minutes at a time. Whatever you make, or whatever resolution or granularity you make your delta t, you want to make sure it's consistent across all your observations. And so in this particular case, when you're counting the single occurrence of this particular event depicted in the example, if delta t represented 2 minutes, then every 2 minutes, I'm going to count the number of events I observe. And so in the case of the customers going through the entry box of a store, you might say, all right, in the first 2 minutes, I saw or counted 5 customers coming in. In the next 2 minutes, I counted 3 customers coming in, and so forth. What's important is that this window of observations, delta t, is of a standard size that you carry on repeatedly. Okay? So we have this observation, and in this particular case, in our window of observation, delta t, we had a single observation, but it's not limited to single. It can be whatever the event, or however the event plays out. And so we have a bunch of windows of observation, delta t. In this particular example, in the first window of observation, we observed 2 events. In the second one, we observed 3 events. In the third one, we observed 4 events. And then that last one, 3 events. But this delta t occurs again and again and again and again and again, and you're just measuring the number of occurrences of an event for whatever your event was. And so we continue measuring the occurrence of our observations, one after the other, continuously over time. Okay, make sense? Any questions? So this is just the setup, the fundamental setup, and it's really important that your delta t doesn't matter what it is, but it must be the same. So the first delta t, if it's 2 minutes, the next one is 2 minutes, and the last one is 2 minutes, and every delta t in between. Any questions? Make sense? Okay. So this is going to help with our notation. And let's think about this. If you're going to measure something that happens the headache is really gone. If you're going to measure something that happens in time, um, how do you do this? How do you measure what happens over a period of time? Because it could be one thing, it could be two things, could be three things. So we're going to need a way to talk about things that happen in time in a standard way so that we can account for the fact that it can occur once, it can occur 10 times within a delta t, it can occur any number of times within a delta t. And so we're going to talk about this quantity we call the rate. And the rate will be a quantity that says, okay, per unit time, what is this notional average of that describes the number of occurrences that we have over that time? So in the case of this first delta t, we have two events over that unit time. So you might say if it were 2 minutes and you had two, you say on average it's one per minute. If you had four and it's 2 minutes, on average it's one every 30 seconds. And so this rate represents a single number that tells us a standard way of talking about events in time because we're talking about delta t and not about a single instant in time. Okay, all right. So we have this idea of a rate, and this rate talks about per period of time. And now, with this idea of a rate, not only can we talk about our probabilities, but we can also actually pose this from actual data that we can sample from things like the camera for the entry box. Or we could talk about space too, but we're gonna kind of leave that aside for now. Okay, so we say per period of time, it's our rate, and we're gonna call our rate R, and R um, rate refers to what's called a module of observation, or sometimes in the literature, you'll read a window of observation. And I try to use synonyms for this so that if you go off and you look at other sources and they're saying it differently, you will at least be familiar with some of that different nomenclature for the same idea. So we have R is a rate, and it corresponds to the frequency of events that occur within a certain module of observation, where each module of observation is our standard delta t that happens again and again and again and again. And we use this delta t, our module, as the means by which we measure, using a single number, the rate, on average, how often we see some event in that period of time. Okay, so one of the things that we might be interested in, if we want to look at this quantity, this number of events in time, this rate is an average, right? It's a gross level description, but you might be interested in how likely or the probability associated with a certain number of events coming in. And the reason for that is you might want to know, gosh, well, if on average somebody spends a certain amount of money, how much money can you expect to collect from your customers, how much revenue. Likewise, if you want to know how many employees you should have for each shift, you might want to know probably this is a stochastic variable, so you want to know if you can expect to make a certain amount of money and you know how much an employee costs per unit time, you can now say, gosh, well, how much can I afford in terms of my employee costs over time? And certainly, if you have a large volume of people coming into your store, you want to have more employees, not only because you can afford them during that period of time, but also because you want to service them faster, right? More employees means better service, faster turnaround, and that means happier customers in general. So of interest, certainly, because the number of people from one instant to the next that can come into your store, that's stochastic. You need to know, or might want to know, it's helpful to know the probability associated with the observation or the observance of a certain number of people for each of those modules. Because while we have this notional average from one instant to the next, you have a number that can change. Okay. So this is what we're interested in. Any questions about this? Make sense? So let's further develop this idea. So, and I forgot what I was going to say here. Okay, yeah, so here are some examples. You have customers that walk into a store. Maybe it's students visiting a dining hall. Or, and this is a really important one, not that the others aren't, the number of packets that arrive in a router, right? And so if you have the expected amount of data that arrives into a router, that helps you choose how much router memory that you have. Because router memory is very expensive, but if you have inadequate router memory, you're going to drop packets because it can't store all of those packets for which it needs to make forwarding decisions. And the result of that is that people using the network say it's slow, right? And in this case, it's slow because it's dropping packets, but users don't care about that. They care about their perceived end-to-end throughput. And so something like this, you would measure the number of packets that come in over some period of time, maybe a day, and you design your delta t. You construct your probability, use a Poisson, and then use it to mimic the packets coming to your routers, and then see how big those buffers could get depending on how many packets need to be stored, and then make a more strategic decision about how much router memory you're gonna buy, right? Because you could just say, let me buy a lot of it, but you never use it and you just wasted your money. Okay, so these are examples for this idea of occurrences of events. And we're going to look at now start to develop the mathematics behind this. So let's define k. It's just a variable, doesn't matter what it is, but k is going to stand for the number of occurrences of interest, right? And so k could be 2 in this case in the first delta t, k is 2. In the second delta t, k is 3. In the third delta t, k is 4, right? So k is the number of occurrences of some event of interest within some window of observation. And so as a probability, we'd want to know the probability that k is equal to 2 or k is equal to 5 or k is equal to 7 or what have you. And we have this notion of an average rate. And so one of the asks that the Poisson addresses is the probability that given a certain average rate, the probability that we're going to observe k at any particular time. Does it make sense? Any questions about this? So this is what the Poisson distribution is doing. And this is what the probability mass function looks like, right? So the probability that you observe k many events within a window of observation, given a rate r, is equal to r to the k power upon k factorial, and then also in the denominator we have e raised to the power r, right? So e to the rate. And so let's kind of deconstruct this. I'll give you the answer first, and then we'll get to that by reducing this to the binomial distribution and taking some limits, and we'll develop all of that. Okay? All right, any questions so far? All right, so this is the probability, the mass function, and that is the probability of observing k events within a window of observation. Okay, so you're like, okay, well, what does that really tell me? So let's take a look, and this is kind of a reminder of the binomial distribution. And with the binomial distribution, if you recall, it said we're going to assume we have a two-way outcome. You could call it flipping a coin. And let's assume that one state of the coin, heads, is a success, and the other state of a coin, tails, is a failure. And so you flip this coin, and what's your n many times? And what you're after with the binomial is the probability that if I flip the coin n many times, given a probability of success of p, what's the likelihood that I'm going to have x many successes? So you have n flips. What's the probability that x of those n flips is going to be a success? Now, if you think about it, the Poisson distribution kind of looks like a binomial. It looks like a really weird binomial. Let's assume that you could flip this coin an infinite number of times. And for every moment in time that you have across your timeline within each delta t, you flip a coin, flip a coin, flip a coin, flip a coin. You constantly flip it, infinite number of times, keep flipping. And whenever you observe an event, that's like having a success, that heads outcome for the coin. And so in that case, you can imagine this as a weird binomial distribution with an infinite number of flips. And then each event that you observe just happens to be one of those successes for the flip. And that's exactly what the Poisson is doing. And so in any discussion or any proof, when you motivate or try to derive what the Poisson distribution is, you start with a binomial, right? And they reuse these things all the time. And let's recall that a binomial is nothing more than a set of Bernoullis, one after the other, after the other, and many times, right? So let's think of the binomial distribution, and then we're going to pose the probability mass function for the binomial, and then we're going to say, let this n, the number of flips, be an infinite number of flips, and it's infinite corresponding to every single instant in time is going to correspond to a two-way outcome, success or not success, or heads or tails for this weird coin experiment. Okay. Any questions about that? Does that make sense? Yes? No? All right. So let's go forward with that. So we have our binomial, and we want to kind of cast this as an infinite binomial with an infinite number of trials, and that'll lead us to the Poisson distribution. So there's the probability mass function for the binomial. It says x is the number of successes, n is the number of flips, right? And p is the probability of success or heads, whatever you want to call it. So if p is the probability of success, 1 minus p by law of total probability is the probability of failure or tails. So if out of those n flips, you get x successes, well, we're going to have the probability p for one success, and you're going to multiply p by itself x many times for each of those x successes, right? So you're going to have p exponentiated to the x power, and then everything else, those n minus x trials where you had a failure, you're going to have 1 minus p. So you multiply 1 minus p times itself, n minus x many times, right, for the remainder of these n flips. So you have x flips out of n are successes, p to the x, and n minus x of these flips were failures. So that's 1 minus p to the n minus x power. Now, this leading coefficient n choose x combination, choosing x out of n, that talks about all the possible arrangements for x successes and n minus x failures. And so we need that leading coefficient to add up, if you will, or count for all those different arrangements that we can have. Okay. Any questions about this? Make sense? To jar your memory? Yeah. Okay. All right. So this is our mass function for the binomial distribution, and we still haven't gotten to the Poisson. But let's recall what we said a slide before, that we're going to think of this Poisson, the observance of events in time, as a sequence of an infinite number of flips. So what we're going to do is we're going to take this binomial, and we're going to account for this weird binomial, this infinite number of flips, by letting this n go to infinity. Okay? And then we're going to see what happens with this mass function and make a few reductions, and we're going to arrive upon the mass function for the Poisson. Okay? All right. So let's first talk about the expectation of a binomial distribution. From before, the expectation is NP, right? We have n Bernoulli trials, and P of them are success. And if you actually do out the math for expectation, you're going to get n times P. Okay. So this is what the expectation is for a binomial. And this average number of successes, that kind of sounds a lot like a rate. On average, how many successes are we going to have? And so what we're going to do is we're going to say, okay, this rate thing that we talked about, the average number of occurrences of an event, if an occurrence of an event is treated like a success in a binomial, then the average number is like this rate. It's the average number of event occurrences. So we're going to take this result, and we're going to set this expectation of the binomial, to be our rate parameter. And we're just going to literally equate the two together. So let's do that. So if NP is equal to R, right, we divide both sides of equality by N, and we get an expression for what this probability of success is for this weird binomial. So if NP is equal to R, that means P is equal to R upon N. Okay. So now what we're going to do is we're going to go forward with this binomial, with this substitution for what P is for the probability of success in the binomial, but now we're going to substitute this R over N everywhere we see P, right? Because they're going to call this average, we're going to call it our rate, and this is the expression we're going to work from. Any questions about this? Does that make sense? Yeah, okay. So going from there, we're just going to make a simple substitution. And so here is our expression for the binomial mass function. And you notice I've replaced P with R upon N here. So I have P to the X, I have R upon N to the X power, and then I have 1 minus P to the N minus X, so that's 1 minus R upon N to the N minus X power. So all I've done is just substituted for this value of P that I arrived upon when I said, okay, this expected number of successes is what I'm going to call my rate, the average number of occurrences of the event, because the occurrence of an event is considered a success when you flip the coin. Okay? All right. Any questions so far? Does that make sense? Okay. So now let's recall when we talked about the fact that this Poisson, the observance of events in time, is the same as a binomial with an infinite number of flips. And this binomial, we said it has n many trials. But now we want to account for this idea of an infinite number of trials. And how we do that is by taking the limit of this expression and let that limit as n goes to infinity, right? As n gets really, really big. And that's the same as saying, how does this binomial distribution work out when we have an infinite number of trials? You can't plug in infinity. What you can do is take the variable in question and let it approach infinity, let it get really, really big, and just take the limit of the resulting expression. Okay, so we take that expression and we say something happens over time. How much time do we assume? Well, of course, at each period of time, we measure what happens. So you can imagine you really, really fast as can possibly be, you flip a coin, flip a coin, flip a coin, flip a coin, every instant in time. An uncountably infinite number of times you're flipping a coin. And you're counting the number of successes. So at each period of time, you measure what happened. And so you see an observation or you don't see an observation. Those are the two alternatives for this weird coin flip. And so that means the number of trials n is infinite. Time marches on. And that's kind of like what the rate means. Rate means regardless of how time marches on, this is kind of the density, if you will, at which you see things happen or don't happen. It's either more packed or more sparse. And so time marches on means infinite. And so now what we're going to do is we take the same expression for the binomial where we substituted for p based on the idea that the average np is equal to our rate. We substituted or that rate, p is r over n, and now we're going to take the limit of this expression as n goes to infinity. So we take the limit of p of x as n goes to infinity, and then we have this distribution, the mass function, and we have this limit as n goes to infinity. If you're going to take the limit of one side of equality, you have to take the limit, the same limit for the other side of equality. Okay, so now we make an observation. We have three terms here. We have the n choose x, that combination. You're multiplying that with the r upon n raised to the x, and you're multiplying that with the 1 minus r upon n raised to the n minus x. So you have the product of three things, and you're taking the limit of the product of three terms. Now, it just so happens that when you take the limit of things that are multiplied together, no, if you make it really big, this is what the expression becomes. So if you take the limit of things multiplied together, that's the same as the limit of each of those things multiplied together. So the limit of the product of things is the same as the product of the limit. So expressed differently, if we take the limit of two functions, f of x and g of x, as n goes to infinity, that's the same as the limit of f of x times the limit of g of x. Does that make sense? Any questions? So that's just saying if I take limit of the product, it's kind of like a distributive property. That limit of, as n goes to infinity, distributes across the multiplication of those two terms, f of x and g of x. And so in this case, when we look at the original expression, I have the limit of the product of three things. The first term here, n choose x. Second term, r upon n to the x. The third term, 1 minus r upon n to the n minus x. So now I'm going to carry out that operation. So what does that mean? So I'm going to take the limit of three things as n goes to infinity. I'm going to take the limit of the n choose x, and then I'm going to show you the limit of the r upon n to the x, and then the limit of the last term, 1 minus r upon n to the n minus x power. So let's take a look at that first term, n choose x. So if we say the limit of n choose x, what does that mean? So if we look at what n choose x is, right, we actually multiply it out and do it out, we get the following expression. N times n minus 1 times n minus 2 times n minus 3, dot, 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 all the way up to n minus x plus 1. And so that results in x minus x terms. So we have the first term, the second term, the third term, the fourth term, and the xth term, right? You could actually do that out and cancel it out. I'm not going to do it here. And then you have the x factorial in the denominator. So if you take a look at the numerator, right, you'll notice that each term has an n in it. There's n, n minus 1, n minus 2, n minus 3, n minus x, blah, 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 right? Now, if you were to multiply these factors out to actually rebuild the polynomial, the first thing you're going to do is multiply n times n times n times n times n, right? And so any polynomial that you create from multiplying these terms together, regardless of how many terms there are, the highest degree in the resulting polynomial is going to have an exponent of x, right? Because it's n times n times n multiplied by itself x many times. To show you a little bit differently, suppose we had x oh, x times x minus 1 times x minus 2, right? I have three terms here, right? And so the first thing I'm going to do, if I'm going to multiply this out, I'm going to multiply x times that x times that x, right? So it's going to be an x cubed. And then when I do this out, I'm not going to do the whole thing out, the leading term is going to have an exponent of 3. And it has to have an exponent of 3 because when I do this multiplication, I'm going to multiply an x. Now let me actually do it out and show you for real. So I multiply this times this, that's x squared minus x, right? And then I multiply by this, so that's x cubed. There's my x cubed. Then I have minus 2x squared minus x squared plus 2x. If I combine these, that's x cubed minus 3x squared plus 2x, right? So there you go. X cubed is my leading term that has an exponent equal to the number of terms that I multiply, and everything else has a lower power of x, right? And so if I write this expression for n choose x, well, by definition of what n choose x is, I'm going to have x terms in the numerator, and when I multiply that out, my leading term for the resulting polynomial is going to have a power of x because I have x terms here. That makes sense? Okay. Any questions? So if my leading term has an exponent of x, everything else has an exponent that's less than x, right? And so here I have my exponent here that's less than 3. This is my exponent of 3. Everything else, every other term, has an exponent that's smaller, right? This is x cubed, there's an x squared, x to the 1 power, right? Okay, make sense? So that being said, okay, so I'm just gonna kind of, because I didn't want to write it all out because I have this can be a lot. So I said, okay, well, if I multiply every term in the numerator, I'm going to have an exponent of x here, so n to the x power, because I have x many terms, each of which has an n in it, right? And then everything else is going to have a value that's less than n to the x, because the exponent is going to be smaller. Does that make sense? Okay, and you see that play out in real terms here. Okay, everything else, I can say this is the same as saying x cubed plus stuff less than x cubed minus 3x squared plus 2x. And that's exactly what I'm doing notationally there. Okay. So I have n to the x power, and then everything else is less than n to the x because it has a smaller power. Okay. If it's negative, it's certainly less. If it's positive, right? Well, it's certainly less because it has a smaller exponent. Okay, so then in the denominator, I still have my x factorial. So now we'll look at what happens when we take this limit. So if we take this limit, well, if we take the limit as as n goes to infinity, well, if we have a higher power here, as n gets bigger and bigger and bigger and bigger, if you raise anything to a higher power, it increases much faster than things that have a lower power, right? And you could even try this out. If I said n cubed plus n squared, and it doesn't matter what the coefficients are. If I said let n equal 1, well, They're very close to one another. So if n equals 1, they're close to one another. Let's say n equals 10. Right? If n equals 10, this is 100. I'm sorry, this is 1,000, and this is 100. This term is 100, and this term is 1,000. If n equals 100, I make it even bigger, right? 100 cubed, so that's 100, 2 zeros, 2 zeros. That's a million. And this one is just 100, 2 zeros. That's 10,000, right? Now, if I make n equal to 1,000, that's 3 zeros. Let's see, 1,000. I add 3 zeros, right? So that's a billion, right? And if I have n equal to 1,000, that's 1,000, 3 zeros, right? That's a million. So as I make n bigger, right, more and more, this term's not even going to matter. What matters is this term, right? So if I said n equals a billion, right, this will have no effect on the sum. If I said n equals a trillion, quadrillion, right? If I said 100 zeros, right, that's getting closer to infinity, but infinity is unbounded. As we increase the value of n here, the value of this expression is dominated by the highest power, and these lower powers become useless, if you will, right? They don't have any effect. So essentially, the value of the expression in the numerator for all the stuff that's less than n to the x, it doesn't even come to play as n gets bigger and bigger and bigger as it approaches infinity. Does that make sense? So that being said, in the limit, as n gets really, really big, this expression we said is n to the x plus stuff less than n to the x over x factorial. Really, it's just equal in the limit to n to the x power over x factorial, because the stuff less than n to the x power doesn't really contribute as n gets bigger and bigger and bigger. Okay? All right. Any questions about this? Okay, so this is the result of the limit for the first term, and we'll do similar with the second term and the third term, unless you take the limit as n approaches to infinity, and we'll multiply those three things together. Okay, so let's take the limit as n goes to infinity of the second term, r upon n to the x. So r upon n to the x power, well, we can take the exponentiation both for the numerator and denominator. So we have r to the x over n to the x, okay? If we take that limit, right? So this is our result, right? It's pretty easy. It's just r to the x over n to the x. Okay. We don't know what r is, but we don't need to know what it is at this moment. So we have these two terms, right? We have n to the x stuff less than n to the x. We have r to the x over n to the x. And remember, the limit of the product of things is the same as the limit of the first thing multiplied with the limit of the second thing multiplied with the limit of the third thing. So we have the two limits of the first two terms. And something interesting is going to happen. Remember, we said the stuff less than n to the x doesn't count in the limit. So we have n to the x over x factorial. We have r to the x over, oh, wait a minute, n to the x. So these n to the x's are going to cancel, right? Because they're both now, you've taken the limit for both of them. You can absolutely cancel them. So you take that limit, and now you have the n to the x here, and here, well, let me just do that and not jump ahead. So we can take this expression and we can collect like terms because it's a multiplication of two fractions. So we have the limit as n goes to infinity, and we have an n to the x. The stuff less than n to the x doesn't count, so we say x factorial. And then we have an r to the x over n to the x. So we can just collect them because they're multiplied together. That's n to the x times r to the x, right? In the denominator, we have x factorial times n to the x. So you can reverse this because multiplication is commutative, right? So we can say n to the x over n to the x, and then we can say r to the x over x factorial. Well, guess what? You have n to the x in both the numerator and denominator, so they cancel to 1. And that's exactly what I've done here in the next step. So we have this limit, and we say that the limit of the product of two things is the same as the limit of the first one times the limit of the second one. And we're just canceling after we do that limit. Okay? So we do that, and we have the common n to the x in the numerator and denominator for the first term, and then we have r to the x upon x factorial for the second term. Any questions about this? Does that make sense? Let me do a time check. Okay, So that being said, we cancel out the first term. That goes to 1. And now we're left with the limit of r to the x over x factorial, right? Because the limit as n goes to infinity of 1 is just 1, right? 1 is a constant, it doesn't change. Okay. So, all right. So we have now taken care of the first two terms, and now we need to take care of that last term. So let's take a look at it first. Any questions right now? Any questions about this? So we're just using algebra, we're using limits, and we're reducing this weird binomial in order to get to this expression for the probability for this Poisson. Okay, so now let's take a look at that last term. So we're going to take the limit as n goes to infinity of this expression, and we said r is a rate. Now a rate is nothing more than a number, and here in this limit, n is going to get really, really, really big. So we're going to take this expression, and we're going to, what did I do here? Oh, yes. So we have 1 minus r upon n, and what did I do there? N to the x is a value. Okay. All right. So in this example, I take my denominator portion. So if we look at this 1 minus r upon n to the n minus x, we can separate that out, 1 minus r upon n to the n power, right, times 1 minus r upon n to the minus x power. And so the part that has this minus x power, right, a minus power is the same as saying 1 over. So I'm just separating out the two terms in terms of the part that's in the numerator and the part that's the denominator. I'm teasing them apart, right? So now I have these two parts. I have the 1 minus r upon n to the n part, and then I have this 1 over 1 upon over 1 minus r upon n to the x part, where the part raised to the x is in the denominator. Okay, so now I take the limit of this whole expression, because again, the limit of one thing, two things multiply is the same as the limit of each one together. So let me take that limit. So let me start with this term, right? So if n goes to infinity, here I have n in the denominator of this expression. And if n gets really, really big, remember r is a rate, right? It's a constant quantity representing the average number of occurrences of events. So essentially, when I say 1 minus r upon n times to the x power, I'm really saying 1 minus r over a really big number. Now, any constant over a really big number goes to 0 as that limit increases, right? So r over really big number goes to 0. So I'm going to substitute that with 0 in the limit, because here r upon n, as n goes to infinity, is r over a really big number. R over a really big number is 0. So I write 1 minus 0, which is 0, right? And I get 0 to the x power. Make sense? So I'm sorry, right? I get 1 to the x power. Let me start that again. So really big, r over really big number is 0. So I get 1 minus 0 to the x power, which is 1 to the x power. Now, 1 times itself doesn't matter how many times, it's always 1, right? Multiplicative identity. So I can replace that 1 to the x power in the denominator with just 1. 1 over 1 is just 1. And guess what? That term goes away. Okay, that was convenient. So now the second part here, limit of 1 minus r upon n raised to the n power. So let's take care of that part. So I'll rewrite it, kind of clean it up a little bit. And I get, as n goes to infinity, 1 minus r over some big number raised to the power of some big number. And you're just going to have to take my word for it. Don't even take my word for it. Google search it. This is a result of something called the Gaussian integral, and we can do out the proof, or post the video, what have you. This is e to the minus r power, right? And that's a classic proof called the Gaussian integrals, where the Gaussian distribution comes from. But nonetheless, there's an identity out there that says when you have 1 minus r over a big number, where r is some constant, and you raise that result to that same big number, it gets e to the minus r. It's actually where e comes from, okay? And so you can replace this other part of the limit with e to the minus r. So let's do that. We won't go today over that identity. So we have the first two terms, which resulted in r to the x over x factorial. And then we have the second term, which is e to the r. So we put them together, and guess what? We have something that looks just like what we were after, whereas here the number of occurrence of events is x, but here we called it k. It doesn't matter what you call the variable. Okay? All right, any questions about this? Does that make sense? So all the Poisson distribution really is a special case of the binomial where you're assuming you're doing an infinite number of coin flips, and what you're counting is the number of occurrences. And how you accomplish that infinite number of coin flips is by letting the number of trials go to infinity. So almost like you're flipping the coin again and again and again and again, really, really fast. And so how you manipulate it is you take your binomial and you let n go to infinity, and you're just using a bunch of manipulations for limits to reduce the expression, and the result is the probability for your Poisson. Okay. Any questions about this? Make sense? And so we're building up machinery so that hopefully the last couple of weeks of the semester, and we have 4.5 weeks left after today, we can actually use some of this to do some modeling, because you can't do the modeling until you build up the machinery. So hopefully we can have some fun doing that this cohort. Okay, so this expression is often rewritten, and we use R because it's convenient to say R for rate, but in the literature they use what's called lambda. It's just a Greek symbol, and they use lambda in place of R to represent this rate. And so here, when you see the Poisson distribution, the probability written for it, this R is replaced with lambda. And so for the full treatment, the probability of observing X events in time, given a rate of lambda, is equal to e to the minus lambda times lambda to the x upon x factorial. And this is the mass function for the Poisson. And so we'll actually use this to do a couple interesting simulations that we can answer questions based on observations. Okay. Any questions about this? And this is the same as the expression from before, only we're replacing r with lambda, literally doing that replacement. Okay. So with that, actually, you know what? Let me see how much time we have. Okay, we have some time. 1:15. So we have a Poisson distribution, and we think that this Poisson is a probability, right? But we're not sure. And to show that any distribution is a probability, you have to show it satisfies the law of total probability. If we add together all of these probabilities, does it equal 1, right? So that's what we're going to make use of. And so notationally, we say some variable x is the observation of the number of occurrences of event, is distributed as, so that tilde, distributed as a Poisson, where lambda is the rate parameter. There's a probability mass function. And so what we're trying to ask to see if it behaves like a probability is if we sum together all these probabilities, does the result equal 1? So if we're observing events, the events we observe can be 0 events, can be 1 event, 2 events, 3 events, 4 events, and so forth. So what we're going to do is we're going to sum together all the probabilities, where that's the probability, the Poisson probability. We're going to sum them together for all occurrences of events, 0 many, 1 many, 2 many, and so forth. So we have this infinite sum, and we're trying to see if that equals 1. And that's where the Taylor series comes in, right? The Taylor series and the Maclaurin series, right? And so we said from before, the Maclaurin polynomial is the same as the Taylor evaluated at 0. And we showed what that was, and we had a MATLAB example of how to do that, okay? And so what we're going to do is use the Taylor series in order to show that this equals to 1. So we're going to compute the infinite sum. That's the total probability. We're going to sum together all of the evaluations for every x, the evaluations of the Poisson probability from that mass function that we just derived. And we're going to now substitute what p of x is. So here p of x is e to the minus lambda, lambda to the x upon x factorial. So we say e to the minus lambda, lambda to the x upon x factorial. So we're going to sum together all of those, and we're going to show that it equals to 1. And we're going to use the Taylor series to demonstrate that. So if, or rather the Maclaurin series to demonstrate. I'm used to saying Taylor series because it's more general, and the Maclaurin series is just the Taylor series evaluated at 0. So I always talk about generals, but we're going to use the Maclaurin series. Okay, so it just so happens, and I encourage you to try this yourself, that the Maclaurin series for e to the lambda is nothing more than the infinite sum of lambda to the x over x factorial. You could actually try this out, right? So you construct your Maclaurin and you take the 0th derivative of e to the lambda, the first, the second, the third, and fourth, and you'll actually find that this is true. And I leave that to you to search for it and to prove it to yourself. Okay. So the Taylor series for e to the lambda, the Maclaurin series for e to the lambda is just this infinite sum of lambda to the x over x factorial. So if we have this expression, we take a look at it, and we see that this e to the lambda, it doesn't involve x. So we have e to the lambda times this expression, and both the numerator and the denominator, lambda to the x and x factorial, both involve x. So because that e to the lambda minus lambda does not have an x anywhere, that's a constant for all intents and purposes for this expression. So we can factor this constant out from the summation, and we'll bring it out front. So we write e to the minus lambda times the infinite sum going from 0 to infinity of lambda to the x upon x factorial, right? And that's just taking advantage of the distributive rule of multiplication over addition. We're factoring out of each term for the sum. So now we look at this and we say, oh, hey, wait a minute. This looks just like the Maclaurin series for e to the lambda. It absolutely is. So we can replace this expression, that was easy, with e to the lambda. So we do that, and we get e to the minus lambda, which was that leading constant, times e to the lambda, which that infinite sum is the Maclaurin series for. And then we just get e to the 0, which is just 1. And there's our proof. Okay? And so our whole reason for going over the Maclaurin series is to show you what it is and what it does. And it actually works with e to the lambda. There's a Maclaurin series for e to the lambda. You could try it out yourself. It absolutely works. You could try the same thing we did for sine x. You do it for e to the x. And it's actually easier because the derivative for e to the x is a lot cleaner. It doesn't cycle like sine x. Okay? All right. Any questions about this? Does that make sense? So because we've shown that we sum up all the probabilities for the Poisson, yeah, you can believe it. This is a probability. It obeys the law of total probability. Okay. Does that make sense? Any questions? So please try it, yourself. It actually is a lot more accessible than it might seem, and it all starts from this binomial distribution. And what you find, and this is on purpose, that a lot of these things kind of build on one another. We started with the Bernoulli distribution, simple heads, tails. And then we put the Bernoulli distributions together and got the binomial. And then we took the binomial, the Bernoulli, we put them together in a sequence of failures and in a success, and we got geometric. And then we took the binomial and we said, okay, what's the number of trials in order to have k successes? And that was negative binomial. And here, we're now taking the binomial and we're doing the infinite number of coin flips over time, and that became our Poisson, right? They're all related to one another. And go to grad school, you'll learn this thing called the regular exponential family and moment generating functions, which kind of beautifully ties everything together. But we reuse what we've done before for the Bernoulli, and this Poisson is nothing more than a special case of the Bernoulli. It's a weird kind of Bernoulli that has an infinite number of trials, and we're just counting the number of heads, if you will, that occur, or the number of successes. Okay. Any questions about this? Does that make sense? So please do go over it and make sure that it makes sense to you, because we will be using this, I promise you that, to do some modeling. Okay. All right, with no further questions, then I think that is everything that I had. All right, so we will pick back up on Thursday. I'll see you Thursday.